In this video, we're going to look at a few more applications of the ratio test. Test the following series for convergence or divergence. Question A, summation n equals 1 to infinity minus 1 to the power of n times n factorial squared divided by 2n factorial. Question B, summation n equals 1 to infinity n factorial divided by 1000 to the power of n. Question C, summation n equals 1 to infinity negative 1 to the power of n times n squared times 4 to the power of n divided by n factorial. Let's look at question A first. Here we have summation n equals 1 to infinity negative 1 to the n times n factorial squared divided by 2n factorial. We will apply the ratio test with a sub n is equal to negative 1 to the power of n times n factorial squared divided by 2n factorial. So applying the ratio test, L is equal to limit n approaches infinity, absolute value of a sub n plus 1 divided by a sub n. This is equal to limit n approaches infinity, absolute value of negative 1. Now, wherever we see a n, we plug in n plus 1 because we're looking at a sub n plus 1. So negative 1 to the power of n plus 1, and we get n plus 1 factorial. So n plus 1 factorial all squared divided by 2 times n plus 1 all factorial. And now we divide by negative 1 to the power of n times n factorial squared divided by 2n factorial. So simplifying, we get absolute value of negative 1 to the power of n plus 1 divided by negative 1 to the power of n times n plus 1 factorial squared. So we can write this as n plus 1 factorial times n plus 1 factorial divided by, and here we have 2 times n plus 1, so the distributed 2, we get 2n plus 2 factorial. And we're going to flip this fraction because we're dividing by this fraction, so we reciprocate it. So multiply by 2n factorial divided by n factorial squared, which is n factorial times n factorial. Now, whenever you're working with these factorial notations, factorial terms, you should always try to simplify it in such a way that we get cancellations. So here we have absolute value of negative 1 to the power of n plus 1 divided by negative 1 to the power of n. Same base, subtract off the exponents. That gives us absolute value of negative 1. Now, we're going to rewrite n plus 1 factorial as n plus 1 times n factorial, so we get a cancellation with the denominator here. Similarly, we're going to rewrite 2n plus 2 factorial as 2n plus 2 times 2n plus 1 times 2n factorial, so we can get a cancellation with the numerator here. So we have n plus 1 times n factorial times n plus 1 times n factorial times 2n factorial divided by, and we have 2n plus 2 factorial. We will simplify it as 2n plus 2 times 2n plus 1 times 2n factorial, and we have n factorial times n factorial. Now we simplify. N factorial in the numerator cancels with n factorial in the denominator. Another n factorial cancels with the numerator and denominator. 2n factorial in the numerator cancels with 2n factorial in the denominator. So we're left with L is equal to, and always put limit as n approaches infinity. So let's also put here limit as n approaches infinity. Don't leave that out. So L is equal to limit as n approaches infinity. Absolute value of negative 1 is just 1. So we just get n plus 1 times n plus 1 divided by 2n plus 2 times 2n plus 1. So we have L is equal to limit as n approaches infinity, n plus 1 times n plus 1 divided by 2n plus 2 times 2n plus 1. This is equal to limit as n approaches infinity. N plus 1 times n plus 1, folding it all out, we get n squared plus 2n plus 1. And in the denominator, we have 2n plus 2 times 2n plus 1, folding it all out, we get 4n squared plus 6n plus 2. And taking the limit as n approaches infinity, we divide by the highest power in the denominator. So divide by n squared, divide by n squared, divide by n squared, and divide all of the numerator by n squared. And we get L is equal to limit as n approaches infinity. N squared divided by n squared is 1, plus 2n divided by n squared is 2 over n, plus 1 over n squared, divided by 4n squared divided by n squared gives us 4. 6n divided by n squared gives us 6 over n, plus 2 over n squared. Now, taking the limit, 2 over n approaches 0 as n approaches infinity. 1 over n squared also approaches 0 as n approaches infinity. 6 over n approaches 0 as n goes to infinity. And 2 over n squared approaches 0 as n approaches infinity. The result is 1/4, which is, of course, less than 1. So since L, the ratio, is equal to 1/4, which is less than 1, the given series, a series summation n equals 1 to infinity, negative 1 to the power of n times n factorial squared divided by 2n factorial converges absolutely by the ratio test. Converges absolutely by the ratio test. All right, let's look at part B. Here we have summation n equals 1 to infinity, n factorial divided by 1000 to the power of n. Let's apply the ratio test with a sub n is equal to n factorial divided by 1000 to the power of n. L is equal to limit n approaches infinity, absolute value of a sub n plus 1 divided by a sub n. This is equal to limit n approaches infinity, n plus 1 factorial. Wherever we see an n, plug in n plus 1 because we're looking at the a sub n plus 1 term. So n plus 1 factorial divided by 1000 to the power of n plus 1 divided by a sub n, which is n factorial, divided by 1000 to the power of n. Notice we didn't write any absolute values because all the terms are positive. N factorial is positive, 1000 to the power of n is positive, and for that reason, we don't need the absolute value. All right, let's simplify this. So we get L is equal to limit n approaches infinity, n plus 1 factorial, divided by 1000 to the power of n plus 1. We're dividing by this fraction, so we reciprocate it, so times 1000 to the power of n divided by n factorial. Now let's simplify it in such a way that we get cancellations. So L is equal to limit as n approaches infinity. We will rewrite n plus 1 factorial as n plus 1 times n factorial. So we can get the cancellation with the denominator. And times 1000 to the power of n divided by 1000 to the power of n plus 1 times n factorial. Now n factorial in the numerator cancels with n factorial in the denominator, and simplifying this further, we get limit n approaches infinity, n plus 1, and now let's simplify 1000 to the n divided by 1000 to the power of n plus 1. They have the same base, subtract off the exponents, so we just get 1000 in the denominator. Now taking the limit as n approaches infinity, the numerator grows to infinity, n plus 1 is a linear function, grows to infinity, and 1000 in the denominator is just a constant, so the ratio approaches infinity. So L is equal to infinity, which is larger than 1, which means the series diverges. It diverges by the ratio test. The series summation n equals 1 to infinity n factorial divided by 1000 to the n diverges by the ratio test. All right, let's look at part C. Here we have summation n equals 1 to infinity negative 1 to the power of n times n squared times 4 to the power of n divided by n factorial. So notice that whenever you see n factorial as part of your series, it's a sure bet that you'll probably be applying the ratio test as a convergence test. All right, so let's apply the ratio test with a sub n is equal to negative 1 to the power of n times n squared times 4 to the power of n divided by n factorial. So L is equal to limit as n approaches infinity, absolute value of a sub n plus 1 divided by a sub n. All right, so we have L is equal to limit as n approaches infinity, absolute value of negative 1 to the power of n plus 1. Wherever we see an n, plug in n plus 1 times n plus 1 all squared times 4 to the power of n plus 1 divided by n plus 1 factorial all divided by negative 1 to the power of n times n squared times 4 to the power of n divided by n factorial. So L is equal to limit as n approaches infinity, absolute value of negative 1 to the power of n plus 1 divided by negative 1 to the power of n, and we get n plus 1 squared, 4 to the power of n plus 1 from the numerator, divided by n plus 1 factorial. We will rewrite this as n plus 1 times n factorial. Let me just rewrite this in a different way, n factorial, and fix this up here, n plus 1, somehow it just got erased, n plus 1 squared. Now, we're dividing by this fraction, that means we reciprocate it. So times n factorial divided by n squared times 4 to the power of n. And we already took care of the negative 1 to the power of n. We've done that here. All right, so let's do a little bit of simplification. Let's check everything. N factorial cancels here in the numerator and denominator. And simplifying this, we get L is equal to limit n approaches infinity of absolute value of negative 1 times n plus 1 squared divided by n squared divided by n plus 1 times n squared times 4 to the n. L is equal to, now absolute value of negative 1 is just 1, so limit n approaches infinity. Let's rewrite this as n plus 1 divided by n all squared. So we're looking at this part here times 1 over n plus 1 times, and we have 4 to the n plus 1 in the numerator. That's what was missing. I was looking for that. So 4 to the power of n plus 1 divided by 4 to the power of n, and same base, subtract off the exponents, we just get 4. All right, so how do we simplify this? Well, we have L is equal to limit n approaches infinity. We can rewrite this as n plus 1 divided by n all squared times 4, and let me just go back to the last page, and times 1 over n plus 1. So L is equal to limit as n approaches infinity. Divide this through, we get n over n, we get 1 plus 1 over n all squared times 4 times 1 over n plus 1. Now, taking the limit as n approaches infinity, we can see that 1 over n is going to go to 0 as n goes to infinity. 1 over n plus 1 will go to 0 as n approaches infinity, because we have 1 divided by n plus 1, which is going to infinity. The result is 0. And 0 is less than 1. So since L is equal to 0, which is less than 1, the series summation n equals 1 to infinity, negative 1 to the power of n, times n squared times 4 to the power of n, divided by n factorial, converges, absolutely, converges, absolutely, by the ratio test. All right, thanks.